Welcome to the day 6 of the 2 questions of physics per day series. In this particular lecture, we are going to solve question 11 and question 12. So question 11 says that let n equals to n naught plus a lambda naught, where lambda naught is the free space wavelength. Lambda naught is the free space wavelength. Then you are required to derive expressions for the phase and group velocity. So for this particular refractive index, we are going to find expressions for phase and group velocity. So this provides a model for refractive index n of a medium as a function of free space wavelength lambda naught, and the relationship is given by the linear equation, okay, where n naught and a are constants. So our objective is to find phase velocity and group velocity for any EM wave, and we will use the fundamental definitions here. Let us see how. So we know that phase velocity is the speed at which the point of the constant phase on a monochromatic waves propagate. Okay, it is defined in the terms of refractive index n, and the speed of light in vacuum c is given by c by n, and it is nothing but phase velocity. Now you have the value of n, and it finally becomes c divided by n naught plus a lambda naught. So this expression shows that phase velocity is independent of the dependent on the wavelength of lambda naught, and it signifies that the medium is dispersive. Okay, so wavelength will be different, then the phase velocity is going to be different, and that is the characteristic of dispersive medium. Now let us move to group velocity. A group velocity is a velocity with which the overall envelope or amplitude of a wave packet propagates. It is defined as d omega by dk. Omega is nothing but angular frequency, k is wave number, and this can be expressed in the term of refractive index by using this particular expression. Okay, so group velocity is given by this expression, and which we need to memorize. But there was one instance when this question was asked as PYQ as well. So to evaluate this expression, we first need to compute the derivative of n with respect to lambda naught. So when we calculate dn divided by d lambda naught, we are going to get a. So we substitute this value a here to finally get that c is group velocity is equal to c divided by n naught plus a lambda naught minus a lambda naught, and a lambda naught minus plus and minus a lambda naught is going to cancel each other, and we are finally left with c divided by n lambda c divided by n naught. So this result indicates that group velocity in this medium is constant and independent of wavelength. So the phase velocity varies with wavelength, confirming the dispersive nature of the medium. So your learning was that whenever we need to ascertain whether the medium is dispersive or not, you will need to establish that whether it depends on the free space wave number or not. If it depends, then it is dispersive. But the sign of A, the sign of constant A determines the type of dispersion. If A is going to get negative and rate of change of dn is also negative, okay, this is normal dispersion. But if they are positive, it is anomalous dispersion. A remarkable feature of this specific linear model is that group velocity is constant and independent of wavelength, while the phase velocity is dependent on wavelength. So you can say that a wave packet which is superposition of different frequencies would propagate through this medium without any distortion of its overall shape, because there is no dispersion for the group, as its all constituent frequencies components travel with the same group velocity. Now let us move to the question 12. For a spherical wave, the displacement phi depends only on r and t, where r is the magnitude of the distance from a fixed point. Obtain a general solution of the wave equation for a spherical wave. So the problem requires us to find the general solution to the wave equation for a spherical wave. A spherical wave is one that propagates radially towards outward from a point, okay, that travels radially outward or inward from a point source. and obviously its wave fronts are spheres, we are given that the wave function phi is spherically symmetric, meaning it depends only on the radial distance r from the origin and the time t. So we know that the three-dimensional wave equation is given by Laplacian of psi equals to 1 by v square and then partial double derivative of psi with respect to t, where v is nothing but the wave propagation speed and the function with which spherical symmetry uh, is valid is because of the Laplacian operator, and which in the spherical symmetry simplifies to this because all the other terms will not exist. So now let us try to put the value of the Laplacian in the given wave equation, and this becomes this, where on the left hand side you have 1 by r square, then partial derivative with respect to r for this whole term within the parenthesis equals to 1 by v square, and then partial double derivative of phi with respect to time. So this equation appears primarily complex, but we can define a new function u. We can define a new function u as a function of r and t such that when you divide u with respect to the radial distance, you will get the phi. Okay. So now let us try to work on the left hand side. So on working on left hand side, we are first required to find the single partial derivative of phi with respect to r. So single partial derivative of phi with respect to r will be simply given by 1 by r, single partial derivative of u with respect to r minus u by r square minus u by r square. Now you will do the little bit mathematical manipulation, and you multiply by r square both to the LHS and RHS to arrive at this particular expression. Now what you will do, you will take the partial derivative of this expression with respect to r to find this, which is actually required in our wave equation because that is the term of the Laplacian. So when you take the partial derivative of this particular form, you get this, which is r times partial derivative of double partial derivative of u with respect to r. Now what you are going to do, you are substitute this value in this given wave equation to arrive at this LHS. Okay, so it is 1 by r and then partial derivative of u with respect to r, and that is double partial derivative. So now we are done with the LHS. Now we will move towards RHS. So you have RHS, you have term in RHS which is double partial derivative of psi with respect to time, and it is simply 1 by r square double partial derivative of u with respect to t. Okay, and we know that we have described that psi is actually u by r. Psi is actually u by r, which we have described here. Okay, so in this way we have this value of RHS, okay, which is 1 upon v square r, then double partial derivative of u with respect to time. Now you have both the LHS and RHS, so you finally compute them, equate them to get this value. Okay, so this is valid for all the region where r is not equal to 0. Okay, and this is a standard one-dimensional wave equation for the function u, which is itself a function of r and t, and r is acting as a spatial variable. The general solution to such equation in general is known as D'Alembert solution. You should always remember that general solution of any equation of this kind, okay, is given by this particular expression, and where you must not forget that psi is u by r. Okay, so u is function which is combination of two functions f and g. F and g are any arbitrary twice differentiable function. Let me tell you, twice differentiable function because it has to be differentiated twice, and from this value of u, you can actually arrive at the expression for the phi r itself. And you know that the first term is actually the term which is for the outgoing spherical wave, and second term actually represents the incoming a spherical wave. Okay, so we can say that the solution consists of two parts. The first term represents an outgoing spherical wave which is propagating away from the origin with speed v, and the second term is the incoming spherical wave which is propagating towards the origin with speed v. Okay, and we know that its amplitude is going to vary as 1 by r. We can ascertain it from the denominator. So we could also finally say that the intensity of such spherical wave falls off as 1 upon r square, which is actually the inverse square law. And let me tell you, intensity of any wave is defined as the quantity which is proportional to the square of the amplitude. Okay, so let us meet in the next lecture.